This is a dead light bulb, and I will tear it down. It's small with a E27 socket, and it's from a German company, Müllerlicht. 5.5 watts, 220 to 240 volts, 50 hertz, yeah, European. E27, I already said that. 38 milliamps. 470 lumens, 2700 K light temperature, and it's dimmable. So we expect a little bit more complicated electronics inside here. Yeah, the number, yeah, Müllerlicht International GmbH. Yeah, address, sorry, and everything, and all the, yeah, stamps you need to sell something electrical in Germany. However, made in People's Republic of China. Okay, how can we get the thing apart? Yeah, let's try squeezing that in the vise. Yeah, the idea is here that it might crack along this line, but who knows? Ooh. Sorry. Yeah. That's it. Nice, huh? So yeah, it's really... So the transparent part is really snapped on, and this board here is glued in. Okay. I need some tools here. Let's start with the... Yeah, I already broken that off by accident with small pliers. Because you see it has an inner aluminium case, which probably goes down all the way to the socket. No, that's not my tactical knife, even if it is from Walter. This is my letter opener. Okay. Yeah, I really don't think we get any further this way. This seems to be silicone, by the way. Ah. Oh yeah, there's a whole lot going on in there. And it's all glued down, the connections. Look at that. I mean, it's made in China, but it's yeah, they spared no expense with the silicone putty. but it comes off really easy from the PCB material. So, wow, okay. If you hope for a short video, you will be disappointed. Ooh, okay. Well, I won't probably completely reverse engineer it, but well, we have a lot of capacitors here for 105 degrees Celsius, so not cheaping out, using an 85 degrees Celsius type, and yeah, I'm pretty sure somewhere the capacity will be printed on. Oh yeah, here. That's 25 volts, 47 microfarads. So this is on the secondary side, I guess, for the LEDs. And this one is... okay, I don't want to destroy it, but... yeah, that's 400 volts. Yeah, you can't read the 4, but it should be 400 volts. 3.3 microfarads. Then we have a small capacitor, ceramic type. And this is... yeah, what is this? I guess an inductor. I only see 2 big pins which relate to that thing. Output diode, bridge rectifier, and controller IC. Can somebody read the type on it? Yeah, I will have to look that up. But that's clearly the intelligence here. Another diode. D2, ZD1, so that's a diode, that's a Zener. Oh yeah. I will not completely reverse engineer that. Partly because it's a small and it's a double-sided board. But yeah, another inductor here. Maybe fuses, heat shrink. And a power tranny. Or MOSFET. Yeah. I'll try to make some photos and get back to you. Oh no, we have here also the board. The connections are also silicon down. Here, made in 2015, on the 17th of December. MK 2835 14E TGP 45. Maybe the board is still working, however there's a dark spot on that LED. you kind of see the traces. Yeah, well, I'll come back to you. So, here's the mess I made, and this is actually the second take of almost everything. There will be an out of sequence clip of me taking the transformer down. Yeah, so I started out, yeah, as you do, taking a nice picture of the board and identifying the chip and mentioning that I won't trace a double-sided board that is populated that densely. So I found a data sheet for the chip, which is, yeah, it's the -00 version. I didn't find a sheet especially for the -30 version, but it's the IW3602-30 on the board from Dialog Semiconductor. So far, so good, and I tried starting to explain it. And then I noticed that the transformer on the board only has 4 pins, and as you can see here in the block diagram, they are using a flyback transformer with a primary winding, a secondary winding, and an auxiliary winding. And yeah, I also found 2 inductivities on the board, but they were slightly different. So, yeah. Okay, enough. Let's dig into it. So that's the driver chip they are using, and it's for dimmable LEDs, and it's quite a beast. It's complicated. So the vendor of the chip thought this thing will drive, and that's the easy part, a flyback converter to drive the LEDs. So in principle, you get your AC mains in, you rectify it, you charge up some capacitor, and then through, in this case, a MOSFET, which is pulsed, you put some energy into the core of your transformer. Okay? This is just a snubber network, so you won't kill your MOSFET down here when it switches off, and yeah, you got a peak voltage here through the inductivity. Yeah, and on the other side, as soon as you switch off, the magnetic field here, which you build up, collapses and induces some voltage here in your secondary, which is rectified and charges another capacitor, and your LEDs light up. That easy. So, current through, electric field builds up, you stop, electric field goes down again, and the electric energy is transferred out through the secondary coil. And you have your auxiliary coil, which delivers energy out, which feeds the chip, rectified of course, and with a capacitor, and also a sense pin proportional to, or inverse proportional to, how much energy you draw out here, electric energy. I mean, yeah, you can only get as much energy out through the two coils in a flyback converter as you put in through your primary coil. So if you draw more out here, less comes out of your auxiliary coil, and the voltage levels here go down. That's simple. Yeah, but this is dimmable. And yeah, a dimmer could just be, you know, a triac cutting off some parts of your AC sine wave. But you don't really can see that after you rectified everything and have it filtered by a big ass capacitor. So they, in addition, have something in front of here after the rectifier, yeah, which you would have some waveform like that here, and there's a diode which isolates any backfeed from the charged up capacitor. So you have some waveform like that here, rectified AC. And through these resistors here, which you can, yeah, it's kind of a current shunt directly, yeah, to ground from the rectified IC that you can switch off via that MOSFET. Okay. And the intelligence here in your LED driver periodically switches in this bleed circuit to get correct voltage measurements of the rectified IC, of the rectified AC. Yeah, there's a V-in feedback pin here. And from that, whatever it sees here, when it puts on some load, some actual load, ohmic load, yeah, not inductive load, not capacitive load, but ohmic load on your mains AC line, yeah, let's say this is really the waveform you're getting after a dimmer, it can learn what the dimmer, which should be somewhere here, actually wants to do. And this is really a beast. So it doesn't not only work for simple triac dimmers, but for all kind of dimmers. So yeah, it's a quite long data sheet. Okay, now for the example circuit, which would be, sorry, that one here. Things get a little bit more complicated. So, yeah, let's put the parts out here, and yeah, I don't know, need everything right now, but you have your two power MOSFETs, which are here and here. One is driving that current shunt through a big, and this is a 1K resistor. Okay, this symmetric or pseudo-symmetric thing here with another 50 ohms here at the source, they didn't do that. So yeah, it's 2 parts less and 1K instead of 750K. You also have this big ass capacitor here. Well, actually it's 3.3 microfarad, 400 volts. Yeah, that's also here. And you have the input inductivities, and that was the first oddity. I could, yeah, it was not that critical, but this is not symmetric. Okay, that's actually a coil. So, yeah, can I get a focus? Oh. Yeah, that's not a resistor, that's a coil. So the only thing that came to me why they would do that is that they really got desperate on the layout and couldn't afford two big inductivities with 4.7 millihenries, or maybe that is a little bit bigger and this is a little bit smaller. Obviously, I cannot measure that one anymore. They do have an X2 capacitor here, also for filtering, and the rest is done in SMD. So on the board, that was the other picture. On one side, you find this bridge rectifier. Everything's there. Also, the feedback here is there. And we have this little tranny in the principal circuit. In theory, the voltage, if you switch that on, the voltage that is creeping in through here is charging up this capacitor and can also jumpstart the circuit. Normally the circuit is supplied, or the chip is supplied by the YCC pin from your auxiliary winding on the flyback transformer. But obviously that's not enough. So in addition, they have this little path here. Yeah, 68 kiloohms, another 68 kiloohms makes about, let's say 120 kiloohms at 240 volts. So an additional about 2 milliampere feet through this transistor to charge that capacitor, which is basically the filter capacitor for the VCC, and is normally fed through the feedback or auxiliary coil through that diode. And they also have a Zener diode to limit the voltage here. So, and that's all on the board. That's basically, where was the Zener? Yeah, that's a Zener diode. So that's also okay. However, this is not a MOSFET. That was on the other side of the board, that tranny. And according to its SMD markings, that's a BJT, which is legitimate. I mean, you can use a MOSFET, but you also can use a BJT. So this capacitor charges up, and at some point it switches through this BJT, which is then charging this capacitor, and we got VCC and get things running. That is, we're starting to modulate that MOSFET on off, so we get some voltage here out of our auxiliary winding. All very nice. And I guess this transistor will be switched off as soon as the V-in pin here sucks some current. So this might not be high impedance. This might be a low impedance input. I haven't really looked it up in the datasheet, or at least the LED driver can switch that in a low impedance or lower impedance mode. I mean, we're talking here 150, 130K, so 280K, so at 250 volts, also less than a milliamp, going here. Yeah, that was all very nice. Oh yeah, one oddity. So here's not a fuse, but here is a 100 ohm resistor. Yeah, that was also throughout all component 100 ohms instead of a fuse. Also limits the inrush current, which is a nice thing. And I get if too much current flows, that thing simply blows up. Anything else? Yeah, I'm missing a capacitor. Initially, I thought this 25 volt, and there it goes. This 25 volt 47 microfarad capacitor was here the output filter capacitor. It's not. Instead of 4.7 microfarads, they have here used 47 microfarads. I don't know why. Guess they have their reasons. Yeah, and then it got complicated because, I mean, really complicated. I mean, the game here with different activities, that's, yeah, a nice enigma, but yeah. But the transformer, that one here, that transformer had only 4 pins. So let's go to work. The first thing to notice is that it's a real nice build. So they even have a little copper band around it. So the build quality, yeah, I guess for shielding, but then it was not earthed in any way. Just another mechanical safeguard. Yeah, I will crack that open off camera this time. Okay, here we go. So yeah, the other 2 pins were right here. So that was one continuous winding. And then we have the next isolation layer. There we have a second winding. And this is thicker wire than this was. So that's the secondary. And this is far too long for a secondary. Yeah. Yeah, let me make some measurements how long these wires were actually. Yeah. And I've written it in here. Yeah. So basically, these are 2 transformer pins, and oh, okay, I haven't put the coil in here. And this is the second coil, another 2 transformer pins. But you need 6 transformer pins. And that's when I stopped the first take and deleted the clips because I got really incoherent. So the thing is, here we have a transformer with 2 coils. And we have we have basically 4 meters of a little bit thicker wire. And we have, that was the inside. And we have about 1.8 meters of thinner wire wound around it, isolated on the outside. And yeah, that's when I started tracing out the board, at least some major components, to find out what's going on. And what's going on with this really, I mean, is a few dozen components on this board. Yeah, really a few dozen components. Even the NTC is there. Yeah, I found it once. It basically looks like a small ceramic SMD cap, but it's there. Yeah, it's there. Yeah, so I traced it out, and the output stage is designed differently. I mean, this gives you a nice isolated output, but in a light bulb, you don't need an isolated output. So maybe you can just use something cheaper here and still use that LED driver. And they came up with the following output stage. Yeah. Wait. Yeah, that will do it. So we have our big ass capacitor here, 400 volts, 3.3 microfarads. And we still have a coil that is driven, yeah, by a MOSFET to ground via a sense resistor. Oh yeah, I forgot to mention that there's a sense resistor here, and there's also a current sense input. So the thing knows how much current it's pulling through that coil. It knows how much, yeah, of the magnetic energy is actually consumed by the LEDs, yeah, through the auxiliary coil, and it knows what the actual AC voltage form is on the input. Sorry, got distracted. So through the coil, and yeah, but the rest is just a simple inverting buck circuit. And I'm trying to take another color here. So in the first cycle, yeah, with the transistor on, current is flowing down here to ground. Okay. As soon as the transistor switches off, current is flowing. Yeah, the coil wants to continue, yeah, to pump the current in that direction. So the current is now flowing through the diode into the filter cap, which is just a big old SMD cap somewhere. Yeah, that's actually the filter cap. So current is then flowing here and charges the filter capacitor, and of course this will be the positive side and this will be the negative side, and that's why they call it, it's an, oh, I'm out of focus. I was out of focus, so I just repeat it. The current flowing in this direction, this will be the positive side of the capacitor, and that's the negative. So LED plus is here. So, and that's why they call it an inverting buck converter. Your plus rail will be the negative, and you generate a second positive rail. Inverting. Took me a while, and of course it's not just a inverting buck converter, but on the same core there is the auxiliary winding, which gives you the V-sense input, yeah, so it can determine how much energy is actually in the core left after the LEDs, yeah, take something out, and the filtering capacitor, and is via a rectifying diode feeding the chip itself. Cheaper. And in addition, this is very nice when you do it this way. You don't need you don't need a snubber circuit for that thing here. You don't need it. Yeah. Okay. I guess there's only one thing left to do, and this is to light up these wonderful LEDs. I suspect they run on 3.2 or maybe 6.4 volts. Yeah, I'm almost sure that they are all in parallel, but we'll see. So I got my good old power supply, my oldest power supply, here with enhanced ammeter. Yeah, there's a current sense amplifier inside a card link. And let's see what the LED board does when we turn up the voltage. So 4 volts is full scale at the moment. And full scale here is 400 milliamps, okay. Maybe I was wrong. And that's all I can do. Yeah, these LEDs, they light up, just light up at, oops, 5 volts. Yeah, you can see it. Can't get a good, yeah. Yeah, yeah. So at 5 volts they light up, and at 5.5 volts they get serious. I mean, like 10 milliamps or so. And the circuit board is built so you have 2 strings of LEDs on both sides. So 1, 2, 3, 4, 5, 6, 7 times 5. So yeah, it would start lighting up at 35 volts, and yeah, I don't have that. Anyway, that was a more complicated teardown than I anticipated of a dimmable LED light bulb. Bye.